Now we're thinking about circular motion, and as you'll see, that's mostly just a new application of some old ideas. Specifically, for the moment, we'll limit our attention to uniform circular motion. Uniform just means constant speed. Now, even though the speed is constant as this object moves along a circular path, there is still acceleration because there's still something about the velocity that is changing, even though speed is not changing. The direction of velocity is changing. Imagine that you're in the car, you're going in a circular path. When you're right here, you're facing in this direction, so at that moment, that's your direction of motion, and when you're right here, you're facing this way, so that's your direction of motion. When you're right here, you're facing this way, so that's your direction of motion. As something moves along a curved path, its direction of motion is always along a line that's tangent to the curve at that moment. So the slopes of the tangent lines are always changing, so the direction of motion is always changing. The direction of velocity is always changing. So in that sense, velocity is always changing, so there's acceleration, and that acceleration must be caused by some kind of net force. Nothing new so far. Let's look in a little more detail at how velocity changes as the thing moves along a circular path. So just imagine when the object is at some point just almost to the top of the circle, and then at some point just a little bit past the top of the circle. So at this time, when it's almost to the top of the circle, the velocity is pointing in this direction, and a very short time after it's past the top of the circle, the velocity is pointing in this direction when the object is right here. So direction of velocity has changed. Right? There has been a change in velocity. The initial velocity and the final velocity are different. And acceleration, remember, is just change in velocity divided by the amount of time it takes to make that change. Let's think about this equation a little bit, and remember that we can rewrite this equation to make it look like this. And then when we look at this, we see that what delta V really means is that it's some extra velocity, some extra new velocity that's added onto the original or initial velocity in order to get a different velocity later on. And let's think of that with arrows representing the velocities. Here's the initial velocity arrow, here's the final velocity arrow. I draw those arrows with the same length because this is uniform circular motion. The moving thing has the same speed all the time, so that means you draw arrows of the same length. The only difference is that those two velocities are pointing in different directions. And here you add some new kind of velocity to the original velocity in order to get a different one. And remember, when you represent addition of vectors and represent it with arrows, the things being added together are connected tail to tip. So if this is the initial velocity and then we have some extra velocity, the delta velocity added on in this direction, right? The things that are being added are connected tail to tip. That means the whole path that you went through for this addition starts here and ends here. So the sum, the net result of that addition, takes us from there to there. So that's VF is the arrow that represents the sum. And this is what you add to the initial velocity in order to get the different final velocity a short time later. But remember, this was happening all around the top of the circle. And right around the top of the circle, it turns out that the extra velocity added on is pointing straight down. In other words, it's pointing directly at the center of the circle. So here's the circle again, and the object has moved a little bit from here to here. Here's the top of the circle. But during that time, the velocity added on was toward the center of the circle. And we know that from way back when we first started thinking about acceleration, the direction of acceleration is the same as the direction of delta v. So acceleration points straight in towards the center of the circle, and Newton's second law tells us that if there is an acceleration, the net force that caused it points the same way. So the net force that is making this acceleration happen points toward the center of the circle. So there's the main idea. If we have something moving in a circular path, there has to be force pointing toward the center of that path in order to make that circular motion happen. And that force pointing in towards the center of the path we call centripetal force. Centripetal force in this case is just a name for how the net force acts in this particular kind of situation. In uniform circular motion with no change in speed, the only kind of change you get in the velocity is change in direction, and it was this force pointing straight in towards the center of the circle. That's what's responsible for changing the direction. That's what's responsible for pulling the moving object into a circular path. And centripetal acceleration just means pointing toward the center, directed towards the center. Now, it's important to note that a centripetal force is not another type of force like gravity or normal force or friction or any of that kind of stuff. What it is just one or more of the forces that we already know about acting in a particular kind of way, acting so as to make circular motion. For example, you've got a star and a planet revolving around that star. Here's the orbit, and it's not, planetary orbits are not perfectly circular, but many of them, like the Earth's, are very close to the circle. And so what is it? What is that force pointing in towards the center of the orbit that is pulling that planet into a circular orbit? Or to put it another way, what kind of force is acting as a centripetal force in this case? And in this case, it would be gravity. The gravitational pull from the star on the planet is what supplies the centripetal force in this case. Or to take another example, let's say you're driving and you make a right turn. And to keep things simple, let's say that while you're turning, the curved path that you're in is circular, approximately 1/4 of a circle. So while you're in a circular path, there has to be some forces must be acting to supply a centripetal force and keep you in that circular path. What's the force in this case? Well, if you weren't moving in a circular path, for instance, if the road were icy and you tried to make this turn, you might slide away from the circular path. So what keeps you in the circular path is some kind of force that prevents sliding. And we know what kind of force prevents sliding. It's static friction. So in this case, static friction is supplying the centripetal force. Static friction is the force that's pointing in towards the center of the circular path. Pointing in towards the center of the circular path so as to push your car into a circular path. Now, let's look at a couple examples in which the centripetal force is supplied not by one force, but by a combination of a couple forces. So let's say you're on a road, a very, very hilly road, and you're coming down to a low point in the road. And right here, right around the low point, the path is approximately circular. You are pretty close to circular motion when you're right here at the low point between the two hills. And what forces are acting on you? Well, of course, there's, as always, weight pulling down and a normal force from the road pushing up. But since you're in a circular path, there must be a centripetal force acting on you. That centripetal force points toward the center of the circle. And if you're moving at a constant speed, there are no forces that are changing your speed. The only forces there are the forces that are changing the direction of your velocity, centripetal force. And as I said before, centripetal force points toward the center of the circular path. So in this case, the net result of these two forces, normal and weight, must be giving you a force toward the center of the circular path. So we'll say that the positive direction is toward the center of the circular path. That's the way we're going to do it always, always, always here when talking about circular motion. The direction, or the positive direction, we always choose to be the direction toward the center of the circular path. That just makes things a lot easier. So the net force on the car in this case is a centripetal force because it's going to be pointing in towards the center of the circle. And as always, it's just adding all the force in the positive direction and subtracting all the force in the negative direction. So it's going to be the normal force in the positive direction, weight in the negative direction, and being a net force, that's equal to mass times acceleration. And there is acceleration because the velocity is changing. The speed isn't changing, but the direction of the velocity is changing. So that acceleration is not zero. So we can rewrite this a little bit, and we see that in this case, normal force equals weight plus ma, and that actually is something there that's not zero, which means, in this case, at this moment, the normal force is stronger than the weight. We've seen all kinds of examples where, vertically speaking, we have just two forces, weight pulling down, normal force pushing up, and then the result of those two is just that they cancel each other out. Here's an example where they are not canceling each other out. They can't, because you've got circular motion, so you know there must be a centripetal force. In other words, there must be net force pointing toward the center of the circle. And in order to have net force pointing toward the center of the circle, the force that points toward the center has to be stronger than the force that points away from the center. Right? You have to have more force toward the center and less force away from the center, so that this force away from the center doesn't cancel out all of the force toward the center, and then you'll still be left with some force toward the center to be the net force that will supply the centripetal force. And now let's look at it from the opposite perspective here. Instead of going through a little valley, imagine going over the top of a hill. So like that. There you are. Just imagine you're at the top of the hill, and at least close to the top, you've got an approximately circular path. You're moving in a circular path, so there is centripetal force acting on you. Whatever forces there are, the net result of those forces has to be a force that points in toward the center of the circle, because without that, there is no circular motion. And the forces acting on you in this case are the same two forces, weight and normal, in the same direction as before. But now, remember, we take the positive direction to be in towards the center of the circle, because that's the way the centripetal acceleration always points. So, in this case, the net force along this direction, which is going to be the centripetal force, because it will be a force that points in toward the center of the circle and makes you move in a circular path, is what? Again, it's just all the force in the positive direction minus all the force in the negative direction. In this case, the force in the positive direction is weight, different from before. And the force in the negative direction is normal. But again, there is a centripetal force. This is a net force, so it's equal to a mass times acceleration. And again, that acceleration is not zero because the velocity is changing. The direction of the velocity is changing, to be specific. So, rewrite this, and we have weight minus NA equals the normal force. Just to move these to opposite sides of the equation. So, in this case, now, the normal force is actually less than the weight, and that's the way it has to be in order to get a centripetal force. Right? The force toward the center of the circle has to be stronger than the force away from the center of the circle. So that the force away from the center cancels out only some of the force toward the center, and then that means there's still some force toward the center left over to be net force. And since that net force points toward the center of the circle, it's a centripetal force. So that's what's responsible for making the car move in a circular path. Right? The combination of weight and normal force in this case is the centripetal force that makes the car move in the circular path. Now, one other thing worth thinking about here. In these cases with centripetal motion, we give a specific name to this particular acceleration, since it's an acceleration caused by a centripetal force. We call it centripetal acceleration. And centripetal acceleration is strictly associated with the circular motion, strictly associated with the change in direction of velocity, because it's caused by the centripetal force, which is what causes the change in direction of velocity. So the centripetal acceleration measures how fast velocity is changing, but in this case the only velocity change is change in direction. So in this case, the centripetal acceleration measures how fast direction of velocity is changing. And we happen to have a nice little rule that connects the value of centripetal acceleration to some other factors. We're moving on a circular path with a radius r, and at some moment you've got a particular velocity and some particular speed. The value of the centripetal acceleration is just square of the speed divided by radius of the circular path. And it's good to understand why this kind of a rule makes sense. Why is it that higher speed means the centripetal acceleration is larger? Why is it that a bigger radius would make the centripetal acceleration smaller? So let's compare two different situations here. Let's say two things moving on the same kind of circular path, right? Two circles with the same radius. But they're moving at different speeds. So we'll call this A, and this is car B, and this one is moving at a constant uniform speed, and it's greater than B's speed. Let's say that we watch A for a little while. We start watching it when it's right here, which means at that moment its velocity is pointing that way, and we watch until it gets here to the far right side of the circle. And of course at that moment the velocity is pointing that way. Velocity, direction of velocity, the direction of motion, is always along a line that's tangent to the circle. And meanwhile, and then we watch B, and we start watching B when it's in the same initial state as A, when it was right up here. So its velocity is again pointing straight horizontally, because that's what the direction tangent to the circle would be at that point. I draw it with a shorter arrow just to indicate that B's speed is less than A's speed. And then I watch it for the same amount of time as I watched A. Like I'm watching them for the same amount of time. So the time interval between the initial and final velocity is the same for both cars. But since B is moving slower, if I watch it for the same amount of time, the thing that moves slower does not travel as far. It's not going to go all the way through a quarter of a circle. It'll go through something less. Let's say it only gets this far. So at that moment, the final velocity points in a direction like that. Now, let's compare the delta V's for the two cases. For A, remember that V initial plus delta V equals V final. The initial velocity was like this, and then the final velocity was like this, same speed, so I want to draw these arrows with the same length. And then what kind of a delta V did I have to add to this in order to get this? Well, it had to have been a velocity like that. And notice again, that's going to be a delta V is in this direction. In other words, it's pointing in towards the center of the circular path again. Delta V points the same way as acceleration, acceleration points the same way as the net force. And there's a net force pointing in towards the center of the circle because it's moving in circular motion. So this is delta V for car A. Delta V for car B, let's think about that. Here's the initial velocity for B. Slower speed, but starts out in the same direction. And then here's the final velocity for B. Try to make them the same length because the speed doesn't change. Again, a shorter arrow because it's moving at a lower speed than A. So, what kind of velocity did I have to add to this in order to get this? What was the delta V for this case? And it's going to be something like that. Again, pointing in towards the center of the circular path. So remember, I added delta V to VI, so those arrows have to be connected tail to tip in the drawing that shows the addition. So there's tip of VI connected to the tail of delta V. Here's the tip of VI connected to the tail of delta V for car B in this case. And then the sum of those two things is the final V, and you'll always represent the sum arrow as starting right at the beginning of the path and going straight to the end of the path, or starting at the beginning of the path and then going straight to where the path ends up. But now look, this is a very short arrow, this is a very long arrow, meaning that the magnitude of this velocity change is a whole lot less than the magnitude of this velocity change. So the acceleration for A is just A's velocity change divided by the length of time you spent watching A, and B's acceleration is the velocity change for B divided by the length of time you spent watching B, which was the same amount of time as A. So same denominator here, but this is much smaller than this. Which means this is smaller than this, so B's acceleration is smaller than A's acceleration. We got smaller acceleration from the thing that was traveling more slowly, moving on the same path, that is, moving on a circle with the same radius, but moving with a slower velocity, smaller acceleration. Just like this says, if two things are moving along the same path, a circle with the same radius, the slower one has a lower centripetal acceleration. That is, the direction of its velocity is changing more slowly. And you can see that because in the time we spent watching the two cars, car A had a lot of velocity change and car B had very little velocity change. And then the last thing to think about when thinking about centripetal acceleration and why it's related to speed and radius, why is it that a larger radius would correspond to a smaller centripetal acceleration? Let's do the same kind of A-B comparison. So let's imagine A is moving on a circular path with a big radius, and then B is moving on a a circular path with a much smaller radius. Radius A bigger than radius B. And now this time, let's say that they both have the same speed. So only the radius of their paths is different for the two cars. And again, do the same thing. Start by watching the two cars, and let's say we start. This time we'll start by watching B, and we start watching at the same location when it's at the top of the circle. So at that moment, velocity is like that, and let's watch until it's gone through 1/4 of the circular path. So we watch until B has gone to this point. We watch until B has gone this far, and when it's at this point, its velocity is represented by a vector like that. Now do the same thing for A. Start watching when it's here, so its velocity is horizontal, but a bigger arrow, an arrow of the same size, because now they're moving at the same speed. So, and then we watch for the same length of time, just like before. So they've got the same speed, and we watch them for the same length of time, so that means they're going to move the same distance. So both of them move this far, but this length on a bigger circle doesn't get you through 1/4 of a circle. It gets you through less than 1/4 of a circle, because this is a bigger circle with bigger radius. So it might only get car A this far. So there's A's final velocity at the end of that much time. So again, let's compare the changes in velocity for A and B. For A, there's the initial velocity, and then there's the final velocity. So what do you have to add to this to get this? The delta V that you add to this to get this is in that direction. Again, the delta V is always, for circular motion, that delta V is always going to be pointing in towards the center of the circle. And then for B, there's the initial velocity, which is just the same as A's initial velocity, because now they have the same speed, and then here's B's final velocity. And to get from this velocity to this velocity, what do we add to this? We added that much extra velocity. So there's delta V for A, just this big, which looks like only about half of delta V for B. So now you got less velocity change for A than you did for B, but you watched them for the same length of time. In the same length of time, A's velocity changed less and B's velocity changed more. So that means the rate of change of B's velocity is higher and the rate of change of A's velocity is lower. The rate of change of A's velocity is just A's acceleration, which is change in velocity over the amount of time you spend watching, and then B's acceleration is the change in B's velocity divided by the time you spend watching, and it's the same amount of time you spend watching in both cases. This is smaller than this, which means this acceleration is smaller than this. the car that was moving on the bigger circular path, the path with a bigger radius, had a smaller acceleration. Bigger radius, smaller acceleration. Because if you're moving on a bigger radius, the curvature of your path is a lot more gentle. And so, since the curvature is a lot more gentle, there's less curvature, so the direction of motion changes more slowly. Whereas on a small circle, the circle with smaller radius, you get bigger acceleration. Bigger acceleration means acceleration is changing faster. And in this case, where speed is not changing, only the direction of velocity is changing, that means direction of velocity is changing faster. And the direction changes faster because it's a much sharper curve. The direction of velocity changes faster on the sharper curve. Okay, so all that is just a way to make sense of why we have this equation. This is one we'll be actually using quite a bit, starting in the next class period.